for the invitation. And this is a work joined with Elena and Edris. Okay? Can you hear me? Okay. Okay. In this work, we are going to present a new continuous data assimilation algorithm for 3D Navier-Stokes alpha model. Just remember, the Navier-Stokes alpha model is given by this system, okay, where U is our filtered velocity, okay. V is U minus alpha squared Laplacian U, where alpha is a constant bigger than 0, okay. This is our system. This is our linear nonlinearity term. P is the pressure, as Navier-Stokes equation. Nu bigger than 0 is our viscosity, and F is our given body forcing. So this equation are a regularization of Navier-Stokes equations in 3 dimensions. And if we take alpha equal to 0, we recover Navier-Stokes equation in 3 dimensions, okay? So we are going to analyze these equations in periodic boundary conditions, where L is the period, okay? We denote V, the set of all L periodic trigonometrical polynomials, okay, that are divergence-free and have 0 average, okay? As the standard literature of Navier-Stokes equations, H is, I'm going to denote as the closure of V in L2, and V, the closure of this V in H1, okay? The well-posedness of these equations was studied by Foyas, Home, and Titi in 2002, okay? So let's talk about the new continuous data assimilation algorithm. It was proposed first by Azoani, Olson, and Titi in 2013. Actually, this paper has already been published, okay? And so how does it work? It works the following way. We consider U of T representing our true evolution of the Navier-Stokes alpha equation in a time t, okay? And we are going to consider IH of U in the time t represent our observational measurements of our system in the time t, okay? And H, it's going to be our spatial resolution of the size H of our measurement, okay? The number of pieces that we are going to have our observational measurement, okay? So the algorithm that we are going to use for construct our approximate solution that we are going to call W of T, that need to converge to UT from the observational measurements is the following. We consider the Navier-Stokes alpha model, okay, with forcing term here, and we add 2 new terms in this equation. This term, okay, where IH of U is what I have already said, is our observations of the system, our measurement, okay, and this term here, where this equation makes sense in the sense of the distribution, okay? And the interesting part of this new system is that our initial condition, W0, can be arbitrarily in an appropriate space. In our case, it's going to be in H1, okay? And Z is our non-filtered velocity of this system, okay? So mu is a parameter that will it will help us to control the system, our relaxation parameter, okay? H bigger than 0 is is going to be another parameter with the dimension of length, okay? And it must be related to H, that is our resolution, how much points we are going to measure. It's going to be related with me in terms of other physical parameters, as viscosity, alpha, forcing term, and the first eigenvalue of the Laplacian that we are calling lambda 1, okay? So this general interpolant that we construct from our observational measurements must satisfy either one or two estimates. IH, we are going to ask for defining in H1, okay, and satisfies this estimate with this norm here, in our case, is equivalent to H1 norm, or IH must be defined on H2, okay, and satisfies for all phi in H2, this is another inequality, okay, this is another estimate. So, I'm going to tell about some examples of these IH interpolants. The first one is the orthogonal projection onto the low Fourier modes. So, since we have phi in H1, we can write phi of this way, okay? And we consider the first n projectiles onto the low Fourier modes, okay? If we define IH of phi this way, the projectiles 1 over h, defined like this, we have that our interpolants IH that must be linear satisfies this estimate, okay? The second example of such interpolants is about volume elements. So how does it work? We take our domain, okay, in our periodic domain, and we divide it in little cubes omega k, okay, in n little cubes omega k, with edge L over cubic root of n, okay? So we are going to define the IH, defined in H1 to L2, as a step function, okay? And the values of the step function is the averages on each little cube that I divided, in each omega k, okay? This symbol stands for the average, okay? So we suppose that the average is known, okay? The average in each little cube is known, okay? Because the averaging of all the function is 0. Now we are considering the space of average is 0. So we proved in this work that our interpolant defined like that satisfies this estimate, okay? The last example of such interpolants is the example of nodal values. How does it work? It works of the following way. We divide again our domain, our periodic boundary domain, in n little cubes, omega k, of the same measure, of the same edge, okay? And we consider xj in omega j as one point in each little cube, okay? And the measurement that the observational measuring that we do in these points, we consider as phi of xj, okay? And we will define IH as the step function again, okay? So we proved in this work also that the interpolant IH defined like this satisfies the second inequality, the second estimate, okay? Just to remember, this norm in our case, since we are considering the space with average 0, this norm is equivalent to the H1 norm, okay? So the equivalent system. To work with these equations, we use the standard functional setting in the Navier-Stokes equations. Using the array projector, we are going to have this system, okay, for Navier-Stokes alpha model for the true evolution, and the approximating solution omega that we construct for any initial condition in this space V H1 shall be given by this system, okay, on the interval 0 capital T, okay. So we have some remarks to talk. If we knew who is the true evolution of Navier-Stokes alpha equation on the initial time, in time t equal to 0, we could take the initial data of this system as the true evolution in the initial time, so the solution W that we are looking for would be equal to the solution U that we are looking, the true evolution of Navier-Stokes alpha equation, okay, for all time by the uniqueness of 9 that I will present the theorem of uniqueness, okay? So we have, but we have a problem. If we knew who is the initial data, okay, the true evolution in the time t equals to 0, we could integrate the Navier-Stokes alpha equation, okay, this, and we don't need any continuous data assimilation, okay, if we knew the true evolution of the initial time. So what the intuition tells us? Oh, okay, so we take, since we can choose any initial condition, so we take the first measurement that we do of the system, okay? You take the time 0, you do the first measurement, okay? The initial observation and the initial observation, and we take this as the initial condition, okay? But we have a problem. If we choose our initial data like this, this may not be an element of the space H1, okay? So the main advantage of this new method is that the results hold when H1 is any element of V, and it can avoid all kinds of difficulties that we have coming from the direct insertion of observational measurement into the approximation solution, okay? Because this is a difficult when we have continuous data assimilation. If we can put the data in the system without problems, okay? So, as I told you, we can choose any initial condition to deal with our system of the approximation solution, okay? Since the initial condition is on the space H1, okay? The V, that is H1 of divergence free. So the difference is that we get our approximation solution, W, using only the observation of the system, okay? And the norm values, because we have this value, the viscosity, first in term, and alpha, okay? So this is our results about this in this work. This is a result of well-posedness, okay? We supposed first, our first theorem, we supposed first that I8 satisfies 3, that is the estimate with H1 norm, okay? And that if we C1 is a constant given by the interpolant, and mu multiplied by H squared must be less than this quantity, okay? If we have this condition, so we have the continuous data assimilation has a unique regular solution. I didn't write, but the space of the solution is W, continuous in time, okay, in V, under L2 in time, dA. The domain of the Laplacian H2, okay? Okay, the second result is the same, is a result of well-posedness, but for I8 satisfying the number 4, the other interpolant, okay? That is the estimate with norm H1 norm and H2 norm, okay? We put two conditions in H for the calculus, okay? And the other result that we got in this work was, in addition to the conditions of uniqueness and the existence and uniqueness, if we have mu bigger than this number, where G is a Grashof the Grashof number, okay, in 3 dimensionals, C is the nonlinearity properties, okay? If we have mu bigger than this value, we have the global unique approximation that we constructed from the observational measurements, W. It satisfies W of t minus U of t, where U of t is the true real evolution of Navier-Stokes alpha equation, goes to 0 in L2 and H1 norms. Okay? So this result is for I8 satisfying the first estimate, okay? This one. Okay? And the second result of convergence that we have is that if I8 satisfies this and not this estimate with H1 norm and H2 norm, we have the following result. We have this result if this is the condition of the existence, the well-posedness for our problem of approximation, and this is the condition for the convergence of W dt to the physical reality or true evolution U, okay, in L2 and H1 norms. Okay? So I don't know if I speak very fast, but it's just, that's it. I have to set up.